This bottle that you see over here, I ran out of Itoen, so it contains water now. Second thing, actually, I'll mention the interview thing tomorrow, next. But I had an interview today, and I was literally asked about RAII. So this is an important topic. This is the single most important C++ idiom that you have to know. Okay? So we're going to talk about that today. Before we begin, I just want to let you take a look at this example. So it's just this really simple function. And the question is, how many code paths are in this function? So what a code path is as you go through the function, how many different ways can like control flow proceed and exit the function? Does that make sense? How many ways can you go through this function? How many different paths can you go through this function and exit?
So do you mean like if we're in the if statement, if like one of the things is true and the other is false? Is that like one path?
Yeah. So for example, one path could be you just skip the if statement completely and you just return. That's one code path. How many code paths are in this code? All right, so I'm hearing 3. Any other answers?
Are we guaranteed valid input? Like, can we immediately throw an error if like we're not putting like an employee?
Interesting question. Without any extra information. 6. Interesting. Okay, I'm wondering where you get these numbers. Okay, so interesting. All right. So who thinks 1? Okay, no one says 1. 2. 2. Okay, so 3. 4. Interesting. More than 4. More than 10. Okay, well, you're all wrong. The answer is definitely more than 10. But first, let's just go through the 3 most obvious ones. Okay, so the most common answer to this question is 3. Let's just quickly walk through it. So you start at the beginning. Okay, you evaluate that. That's false. So we evaluate the other expression. That's also false. So we return. That's one code path. Okay. Second code path. We start this function. This part returns true. What happens when this returns true? Yeah. Exactly, short-circuiting. Because they're short-circuiting, you don't evaluate the other part. Now actually, if the first one is false, if the second one is true, then you evaluate this part, and then you exit. Okay? Third part is exactly what you said. If this is true, then we don't have to evaluate the second part, so you evaluate this part, return. Okay? So 3 code paths. I'm just curious, what is the fourth? For those of you who answered 4, what's the fourth one?
I thought you wouldn't short-circuit it if they're both true.
Oh, okay, I see. Any other code paths? You mentioned 6.
I thought the first and last were different things.
Oh, I see. Okay. All right. So, are there any other code paths?
Well, you said there's more than 10.
Mm-hmm.
So
Yes.
yes.
Okay.
Identify those? No.
Okay. So where would they come from? And the hint is,
Oh, is it within the other calls of the function?
you can assume those calls are like atomic. It's like you're just making the function call. Don't think too much about what's happening in the call. Yeah. Is there any way to exit this function anywhere besides the return statement?
Throw an error?
You can throw an error, right? You can throw exceptions. How many places could this code, without any extra information, how many places could this code throw exceptions? So the answer is 23 minus 3. So 20. There's 20 different places this code could throw exceptions. All right, let's just quickly walk through the code. Okay, so employee E. Could an exception be thrown here?
Invalid input?
Okay, so what function is called here? There's a function that's called here.
A copy constructor?
Yeah, so exactly. As the copy constructor is called, if the input is invalid, then this could throw an exception. Okay, so that's one place. What's the next place that an exception could be thrown? E.title, that could throw an exception. Okay, anything else?
Equals
So even though this is equals, ideally this probably works, but you actually don't know what e.title returns. It could return a string. It could also return something that's not a string, and then the user overloaded equals. Okay? No idea why you would want to do that, but possibly that's possible. So equals could also throw an exception. Same thing over here. Salary could throw an exception. Greater than could throw an exception if the user overloads all of those. Right? You're not told any extra information. Could the or sign throw an exception? So you can actually overload the you can overload the or operator. I don't know why you would want to do that, but you can overload the or operator. So another place you can throw an exception. All right, how about these? Can you throw exceptions here? Okay, how many times can you throw an exception over inside here? So e dot first, you can definitely throw an exception there. E dot last, you can throw an exception there. Any other places you can throw exceptions? Okay, every time you call the stream insertion operator, you can throw an exception there, right? You can, suppose you try to print something to see out, and then your whatever object is invalid. So each of these can also throw an exception. 1, 2, 3, 4, 5. Those could all throw an exception. Anywhere else? Okay, yeah, so e dot first throw an exception, e dot last you can throw an exception. The pluses could be user defined, right? Because even though, okay, if this is a string, then string plus string, okay, that's a C++ thing, that won't throw an exception. But you might have not string, this might not be a string, plus a string, then the user defines, okay, the user can overload the plus operator. So you can throw an exception there, and you can also throw an exception there. Okay? One more place. Return, yeah, return calls what? Return calls copy constructor for the string. I think the string does the string does throw an exception for some values. All right. So the answer is at least 23. Good question. Could there be more than 23? Which functions could be throwing? We haven't talked about destructors, right? So there's a lot of destructors going on. There's this, well, I think there's one destructor. I'm not sure about the other ones. This employee object, when it reaches here, is also destructed. So that could throw an exception. Usually we assume that destructors don't throw exceptions because weird things happen if destructors throw exceptions. Okay? So if you add all those up, there are at least 23 code paths. All right? 3 obvious ones and then 20 due to exceptions. Now, okay, now you might wonder, okay, so who cares? Right? There's 23 exceptions, the 23 code paths. Why does this matter? Okay, follow-up question. Suppose you had this code. And the question is, can you guarantee that there is no memory leak in this code?
I don't understand how you could delete something and then return it.
Oh, my bad. That's not delete. That should be E. Okay, change that to an E. Sorry. I copy-pasted it incorrectly. This should be an E. So it's deleting the pointer. Is there a markup thing I can do? Change this to an E. There we go. Okay. All right. So you're calling new here. So we're allocating something on the heap. We're doing a bunch of stuff with it. Okay. These should be arrows. My apologies. I made this really late last night. Okay, these should be arrows. These should be arrows. These should all be arrows. Okay. So, is there a memory leak here?
Could you define what you mean by memory leak?
So, I'm allocating stuff on the heap over here. Am I guaranteed that by the time this function ends, I return the memory, I free the memory? So for the 3 normal code paths, yes, because you call delete result. You call delete eat here. So when you call new, you allocate memory on the heap. When you call delete, you free the memory on the heap, right? So for normal exceptions, for normal control, normal code paths for the 3 that we talked about, that's fine. What about for the other 20? So for example, if I call new here, and then if I tried to do e arrow title, if this throws an exception, we exit this function and we don't even reach the delete E. Does that make sense? Right? The important part about why these 20 code paths are important is that if we are going through all these 20 other code paths, it might not necessarily reach this delete E, in which case we have a memory leak. Okay? So that's a big problem, and given all the tools you have right now, you actually don't know how to solve this, right? Yeah, question? Uh-huh.
Why is it bad to have the memory leak? Because like this is just one function. This employee is like constructed newly every time the function is called. So like just having that in heap, is that like bad?
Yeah, so I think 106B talked about memory leaks, right? 106X talked about memory leaks. Wait, Cynthia did not talk about memory leaks? What?
Okay, I can sort of provide like a brief.
Okay, huh.
Okay, yeah, going back. Yeah, so actually, this is a good general question of like, why is it that memory leaks are bad in general? There's a couple different reasons. One of them is actually there are a large number of security vulnerabilities that are based on the fact that memory can be leaked. And I won't go into those now, but if you search them, you'll realize that in general, this sort of unspecified behavior is really bad. Another sort of more practical one that you might be more familiar with just in terms of programming is that, let's say, like, for example, here we're only creating one new employee, but let's say we happen to call this function 1,000,000 times, as may happen, for example, in something as large as like Google, where they have like more than 1,000,000 transactions going on every day. In that case, soon you'll have, so what happens when you don't free this pointer is that your computer will treat it as memory that can no longer be allocated. Meaning that if you call this 1,000,000 times and your computer doesn't have space more than 1,000,000 times like a byte of space, then your computer will run out of RAM to work with. So that's one example of where memory leaks go wrong. And there's a lot of other sort of either small or big implications of having memory leaks. It's a valid question, but yes, it's one of sort of the big canonical rules of programming. It's like you don't want memory leaks.
Okay. Do we want like a quick refresh on what memory leaks are? Just a quick definition? No? Okay. Because if you're doing tiles right now, you don't want memory leaks in tiles. You're all doing tiles right now, right? Okay. Don't have memory leaks in tiles. Yeah. So a memory leak is when you know how if you normally declare variables on the stack, then their lifetime is that function call, right? And then when the function's done, that memory is freed. If you use the keyword new, like what you've been doing with like list nodes, those are allocated on the heap. So these objects, they persist. Nice hat. So their lifetime persists even after the function is done. The problem is because if you declare something on the heap, it will not be automatically freed for you. You have to free it yourself. Imagine what happens if we constantly try to allocate more and more memory, and then if you keep allocating memory here, this pointer is going to the pointer no longer exists after the function is done, but the pointer was originally pointing to memory on the heap that was allocated, right? So if the function is done, you no longer have the pointer, you just have allocated memory on the heap that you can't access, but the operating system doesn't know you have to free that.
Yeah. So what the delete keyword does is it essentially tells your operating system, hey, you can reuse that memory again. Otherwise, your system will assume that it's still in use.
So if I terminate the whole program, will it free by itself? Like I terminate the whole program.
I don't think so, right? I don't think so.
I think
Jerry said yes?
For
Okay.
the entire program, it does clean up everything.
Okay.
But for a specific function, for the lifetime of the program, it will not.
Yeah. I think this is one of the reasons Google Chrome is really slow. So if you open a lot of tabs, and then if you don't fully quit Google Chrome, it gets slower and slower and slower over time. Yeah, and I think I read somewhere that the reason is because it has massive memory leaks. Now it's not super important; it still works, but it's just you get memory that's being wasted. It can no longer be used, but it's not being recycled either. Okay, so that's why memory leaks are bad. Yeah, so the thing here is you cannot guarantee that this function does not have a memory leak, because if the code throws an exception anywhere here, so from here all the way down to here, if an exception is thrown anywhere between here, then you skip the result, the delete E line. Okay, so this function could have a memory leak, especially if exceptions are thrown. Okay, So how do we tackle that? A more general concern is oftentimes in C++, there are these resources which you can acquire them, but once you acquire them, you have to remember to release them later so that some other, either another program, some other function are able to use that memory. Okay, so heap memory is one example where you can acquire heap memory using new, and then you can release it using delete. Are there any other resources where if you acquire it, you have to remember to release it? There's one big one that we talked about in Windows XL. Ideas? Yeah.
Streams.
Exactly. Streams. All right. When do you acquire something in a stream? For example, an example is for file streams. What do they acquire? A file stream acquires something when it opens a file, right? When it calls .open, then it has possession over that file. It can read from the file. And then when you're done reading from the file, what do you have to remember to do? You have to close the file, right? Okay, so yeah, those are some other examples. Files, when you open a file, you have to remember to close it. Okay. Similarly, there are other things. These are things called locks. Anyone here in 110? No? Okay. So actually, Anna might talk about multi-threading next time, but locks are essentially when you have multiple programs trying to run at the same time. You sometimes need a lock to prevent both of them from competing over the same data structure. So if both of them are trying to edit the same data structure, you need to use a lock to prevent one of them from accessing while the other one is writing. Does that make sense? So what a lock does is these different functions, they can try to acquire a lock, which essentially they have possession of the lock. The other threads cannot do anything. And then when they're done with it, they have to unlock. Okay? You can imagine how bad it is if you locked something and then you don't unlock it, right? Yeah, sockets. We're not going to talk too much about sockets. So just as a quick aside, we're not going to go too much in depth into exceptions, but exceptions are just a way for you to transfer control and information to this thing called an exception handler. Okay? You've used exceptions in 106B, the throw keyword. Yeah. Okay. You never had to write this try catch thing, but I think the starter code for like the main file, they have like a try catch inside of them, so that if you throw an exception over here, then it's able to catch that kind of exception. All right. This was taught in 106A, I think, if you took it with Java. Vaguely remember this? Maybe. Okay. So yeah, that's a way to handle exceptions. We're not going to talk too much about exceptions because 106B kind of teaches it, and they're also really easy to figure out. It's literally just a bunch of syntax. So we're not going to go too much in depth of that. But the idea of exception safety, where you have to be careful if an exception is thrown, that's a very important idea in object-oriented programming. Okay, so here we can't guarantee that this delete, I have to change all these, this delete is called when the function exits, because you might exit the function sometime over here. Does that make sense? Any questions? What questions do you have? Yeah. Uh-huh.
The exceptions don't necessarily kill the entire program?
No, because what you can do is when you do throw, it exits the function, but then if you wrap it within a try catch, if you can wrap whatever code in a try catch statement, if you throw something, then the control flow immediately goes to one of these catch statements based on what exception you threw.
If it's like, so exception like kills the function that you're currently in, but then it goes to the next catch?
Actually, so you can put whatever, you can put a throw statement in here, for example, and then if you throw an exception, then one of these will catch it depending on what kind of exception it is. Yeah. Does that make sense? Yeah. We're not going to go too much in depth into exactly how they work because they're really easy to Google. There's nothing too hard about exceptions. It's literally just syntax. So, but the idea of how you have to protect against exceptions is very important. So, how do we guarantee that a class releases a resource regardless of exceptions? Okay, so even if an exception is thrown over here, I want to make sure that I release the memory, the heap memory that I allocated over here. All right. So, just as an aside, there's also this other concept called exception safety, where one way to solve this problem is you can say, hey, these functions, you're not allowed to throw exceptions. Okay? You can tell a function, you cannot throw an exception. That was what we've done in the no-throw keyword. Remember the no-throw keyword that I was a little confused about a couple lectures ago? Yeah. There are some functions where you should absolutely not throw exceptions because that causes like undefined behavior. For example, if you throw an exception in the destructor, then you're kind of wondering like, okay, so like, is this object actually destroyed or is it still somewhere, right? If you stop halfway in the destructor, what does that mean? Yeah, so because that doesn't really, there's no real logical meaning for that, you're not allowed to throw in destructors. Same thing for like swaps, for move constructors, you're not allowed to throw in any of those. Okay, so that's called the no-throw exception guarantee. There are also less other types of guarantees, like strong exceptions, basic exceptions, no exceptions, okay? Today, we want to try to write code which will satisfy this basic exception guarantee, where you're guaranteed that even if an exception is thrown, your program is still in a valid state. You can still recover from it, okay? All right. Another way to avoid problems like this is avoiding exceptions entirely. So this snippet comes from the Google style guide. So Google does not use exceptions, at least for C++. Okay, and their reason's actually really funny. You can read all about it here. You can read it at the link. But the reason is we forgot to do it initially when they first developed C++, when they first developed Google, so they're not even going to start bothering. Okay, what's hard about dealing with exceptions is if some of your code doesn't handle exceptions well, then you can't really throw exceptions if you write new code. Okay, does that make sense? So some companies literally ban exceptions, but exceptions are very powerful. So you still should learn how to use exceptions. Yeah, question.
Is there some fundamental reason why it is difficult to add exceptions to new code?
Yeah, because part of it's kind of the reason over here, which is if you allow exceptions, then you're not guaranteed that you will free this resource.
Okay.
Yeah, like
the entire architecture needs to be changed.
exactly. So for example, then you can't use file streams can't be used safely because if you throw an exception, the stream could still be accessing some file. Yeah, then that's bad. So if you want to make it so that you can use exceptions, you have to make sure that that you are able to handle this problem. Okay? All right, let's talk about how to handle this problem. Okay, this is a technique called RAII. It stands for Resource Acquisition is Initialization. Okay, do I have a side note? Okay, yeah, I have a side note here. The father of C++, I forgot how to pronounce his name. This was his explanation of why it's named RAII. Okay, so I'm gonna explain what RAII is soon, and you'll see that this doesn't, well, it kind of makes sense, but it doesn't really capture the full picture, okay? A better name for this is SBRM. Also, the M should not be highlighted, the R should be highlighted. Scope-based memory management. So scope is going to be really important here. We're going to use ideas from scope to be able to automatically free memory. My favorite name is Cadre, yes, Cadre. Yeah, it stands for Constructor Acquires Destructor Releases. Just from this, can you kind of guess what RAII means?
So these are all the same thing.
Yes. This is the best name for it. In a nutshell, what does this mean?
Always have a destructor for every constructor.
Okay. Yeah. So when you're creating the object, you know that there is when the object is created, there's a constructor, and you know that when the object goes out of scope, there's a destructor. Okay. Because the destructor is always called when you go out of scope, you can put the code for releasing resources in the destructor. Does that make sense? Okay, so just as a recap, if you go back here, if you put the delete here, the problem with that is it might not be called even when the memory goes out of scope. So what's better is you can put the code for releasing the resource in the destructor. That way, no matter what, if you exit the function, the resource will be released. Question, yeah.
So what if you want to release it prior to it going out of scope?
That's a good question. So you generally want to. There's some ways around that. There is a way where you can set it so that you can create like your own scope. Did you know you can actually put the braces just there and it creates like its own scope? Yeah. So you might sometimes wonder, okay, why do you sometimes just see random curly braces sitting there? And the reason is because those create like an inner scope. If you declare objects within that, it gets released when that function is done. Yeah. You want to be careful about like having the release in the destructor, but also having the release in like somewhere else, because then you might get issues of like, okay, are you releasing it twice? Are you releasing it once? Yeah. So yeah, go on.
Oh yeah, so generally like you would still only have it released in the destructor, but you could potentially play around with scope to change where it releases.
Does this make sense? Okay. I know it's really boring. You all look super bored, but this is a really important. This is a really important example. Okay, so this is not related to RAII, but since we're on the topic of bad acronyms, here's another one. And I'm serious. This is an actual idiom. It's called pointer to implementation, and they decided to name it pimple.
Potential final topic if you guys are actually interested.
Yeah. So what happens is in the class itself, you'll actually see pimple, and it actually has a meaning. It means pointer to implementation. So you'll actually see pimple in code. Okay. If you do a Control F on whatever code base, you'll see pimple. If you type in pimple, you'll see it appear many times. Okay. You can never get rid of it. Cool. So RAII, the idea is if you acquire a resource, you should always do it in the constructor. If you release a resource, you do it in the destructor. Okay. The rationale, you want to put it in the constructor so that there's never like a half valid state. Once the constructor is done, the resource is ready to be used. And then the destructor, you always call the destructor when it goes out of scope. So you should put the release of the resource in the destructor. As an example, you learned this code in CS106B, right? This vaguely familiar? Right? You're opening a file and then reading it line by line, printing it, and then closing it. Is this RAII compliant? Why is it not? Yeah. So what you notice here is that you're acquiring the resource, not in the constructor, but you're acquiring it in a separate function call. And then you're releasing the resource, not in the destructor, but you're releasing it in a separate function call. Okay? Now, this is really interesting because, like, I'm sure you've sometimes forgotten to put the close, but your code still works if you forget to put the close. All right? Whoever implemented the stream libraries in the destructor, they do close the file for you if you haven't closed it already. Okay, so this is the correct RAII code. The file stream library is already RAII compliant. It's just for backwards compatibility, they give an open and a close function just so that it doesn't break existing code. But you should not use open and close.
Like at all, no more.
No, you should not use it at all. You should immediately, when you create your if stream, you should immediately just pass in the file name, which by the time this object is created, the if stream is valid. Okay, that also ensures that there's no like invalid code. So for example, if you put something in between here, then that might be invalid because you haven't actually acquired your resource. So to put it here, then you're guaranteed that whenever you use input, it will be valid at this point. And then we don't need a close call because the stream destructor releases it. Okay. One quarter, I had an argument with the lecturer, which is like they decided to deduct a point if you forgot to call close, and then I'm like, well, you're not supposed to call close. Okay. Yeah. So you should not be calling close. It's fine if you call close, but in reality, the if stream class is RAII compliant. So even if you throw an exception like here, you're guaranteed that even as you leave this function, the stream is closed. Okay, here's another example. We don't want to talk too much about locks, but a mutex is basically a lock. So you can say, okay, I want to lock the lock, change the database, and then unlock the database. Is this RAII compliant? No, because you actually have a function call for acquiring and releasing. Okay, so what's a better way? You can use this thing called a lock guard. Okay, so lock guard is really cute. What it does, it has one function only. It basically takes in the lock, and it basically just keeps it until the lock guard is destructed, and then it releases it. It does not do anything other than get control of the lock, hold it until its destructor is called, and then it releases the lock. That way you're guaranteed that even if you throw an exception here, you will always release the lock.
And if you guys go on to 110, you will absolutely be using the lock guard. So you will come back.
Yeah,
Come back and
like
remember this.
this is a real C++ code. So, okay, cool thing. I was having an interview today, and they literally asked me, why do you use a lock guard? And I was like, oh yeah, should I pull up my slides? Okay, so yeah, people do actually, this is actually a super important thing. So lock guards are super important. Okay, do I want to talk about this? Okay, sure. How do you think a lock guard is implemented? It looks like this. It literally has two methods, a constructor, which takes in the lock, and it saves the lock, and it remembers to lock the lock. And then in its destructor, it unlocks the lock. Question, yeah?
Can you just reiterate what lock actually does to prevent it from being...
Oh, okay, that's a good, all right, let me do an example. So suppose Anna, okay, so just to simulate what a multi-threaded program is, suppose Anna and I are both trying to access this jar of candy, okay? Your job, Anna's job is to count how many pieces of candy are in there. My job is to take candy from the jar.
I want to make sure Avery hasn't been taking candy, but who knows?
Okay. Yeah. So imagine both of us trying to do it at the same time, right? So you're trying to count, but I'm trying to take stuff out, right? Yeah. So like that kind of destroys the integrity of this data structure because you're trying to count stuff, but I'm trying to remove stuff from it. Yeah. So.
This is a state.
Yeah. So what a lock does is it's kind of like a permission slip. Yeah. Who like for whoever reaches this grabs it, and then the other person has to wait until I release it. Yeah. Think of it like a permit. You have to grab the permit before you can do stuff with this data structure. And then every time when you're done, you have to release it so that someone else can use the permit. Okay?
Which is why not using the RAII lock guard and potentially having your unlock function never be called is so dangerous because it means that if, say, just a single thread ever happens to exit before that unlock is called, then no other thread can ever access that again. Yeah.
Yeah. So the analogy would be,
No one can ever get
yeah.
it.
So the analogy is if I tried grabbing this and then I suddenly trip and I fall, and I just lie there, then this jar is going to be sitting there, but Anna can never reach it. Anna will just be waiting for eternity.
Is there a way to get around that? Like, because if let's say you were storing an important database, and something like that just happens, is there a backup way to?
So if you're, oh yeah.
Oh, I was just going to say RAII, but go on. Yeah.
So that's a good point there. In that case, when the program ends, the locks destructors everything would be reset in the same way that yeah. So you could just restart your program. But
Right.
yes.
Mm-hmm. Yeah, like you don't really want to restart Google, right?
Exactly.
Yeah. So yeah, make sure you follow stuff like this so that no, even if I fall, this is returned to here where someone else can still take the permit.
When we say eternity, we usually mean like the duration of the program.
Mm-hmm.
Quite a long.
Question? Yeah.
So what if we have some code after the original unlock? Like, originally if we do lock unlock, right? After unlock, the other threads can already access.
Exactly.
Mm-hmm. Yeah. When you call unlock, the other thread is then able to
But
access.
In this case, like we have a bracket, and the login will be valid throughout the whole
Yeah,
in the
exactly.
bracket, right?
So if you need the lock guard to be ended, that was sort of what Zach's question was. You could define your own inner scope, so that destructor would be called, and you could then have other threads access it.
I can try typing it out. It's not open, huh? Okay. Almost done. Just a quick side note: mutexes are special. They can't be copied and they can't be moved, right? Because imagine if you tried copying that, then it kind of destroys the integrity of this whole thing, right? If I make multiple permits, then that kind of defeats the purpose. If you're able to just move this to somewhere else, that also defeats the purpose. So mutexes can't be copied, and that's why you have to use this reference thing, which is why an initializer list is important. Coming back full circle. Okay. Yeah. Cool. Summary. Okay. So the question is about memory. And here was an article title posted last year. Just look at the date. Yeah, so this was a half-hearted April Fool's joke about something which has some truth in it. All right, so C++ will no longer have pointers. Anna will soon be talking about this idea about taking memory management and making it automatic using RAII. Okay, so if you look at the style guide for C++, it says you should not be calling new and delete explicitly. Just like you should not be calling open and close, you should not be calling lock and unlock, you should not be calling new and delete explicitly. So, Anna's turn.
Yeah, and that's so important actually that that's going to be the final thing we end on today. As in not right now when I finish my slides.
Do you want to use? You're using yours. Right?
Yeah, no.
Okay. Just want to mention one more thing about automatic memory management. People hate on C++ all the time because it has no memory management. But one argument against that, which you can tell to your Python friends, is that automatic memory management is sometimes not a good thing. Okay. For example, in Java has a garbage collector. The issue with the garbage collector is you actually don't know when the object itself is going to be freed. There's no determination of when the object is actually being freed. The object will be freed, but you don't know when that will happen. It's not deterministic. Unlike RAII, where you're guaranteed in the destructor, which will always be called when it goes out of scope, that's when your object will be freed. Okay? So that's one thing about why Java is bad. Okay, I'm done with that. Yeah, I should do it.
Yeah.
Should I keep these annotations
I think we have
recording?
time.
Okay, cool.
Okay, awesome. So this is sort of the reason why Avery and I are both like, this is one of the most important lectures, because this is actually one of the biggest style changes in modern C++ that have come out of each new C++ generation. So like this is I think one of the biggest stylistic differences from what you learn in B or X to what people actually use in industry. And it goes back to the whole thing that you just saw of basically in real life now using modern C++, you will almost never use a new or delete. And that's crazy. And the reason why we don't have to is because of what we're about to cover. So as a sort of brief review from a couple minutes ago in this lecture, we've seen up till now how file reading and locks can be non-RAII compliant. So in this case, the two commands were open and close or lock and unlock. And the way that we fixed it was by creating this new object within C++ that ensures that the resource is released in the destructor. So in this case, it's sort of a wrapper object. In this case, the IF stream already being a wrapper object. And in this case, a new class called a lock guard, which again, as Avery said, the only thing it does is it acquires the lock in the constructor and releases it in the destructor, ensuring that it will always be released. So there's one more place that we can apply this, and you guys have already seen this. So how many people does this look familiar to? Have people seen this? Okay, perfect. Is this RAII compliant? No. Okay. And exactly. And the reason is because, as we've seen before, if while we're doing all this stuff with this pointer that we've created, if somewhere an exception is thrown, then we're not guaranteed that n is deleted. So does anyone have a thought on how we might be able to fix this, just in general terms? Say it louder. Yeah, Brennan. Oh. Yeah, no, say it louder.
Whenever exit scope, just have it delete from the destructor
So how can we ensure that whenever it exits, in what destructor?
of the node type.
So we could, so that is a good, so notice though, however, that in this case, what we want to delete isn't the node itself. We're not calling delete on the node. What are we calling delete on? On the pointer, exactly. So sort of following the same idea where the fix was to wrap it in an object, in another object in C++ that does all of this logic for us. In this case, the exact same idea, we're gonna wrap it in another C++ object called smart pointers. that will ensure that it does this exact thing for us. So we won't have time today, but I'm going to release the code after lecture.
It's releasing it.
No, we don't have time for it. So we won't have time, but after code, after lecture, I'll release the code. It's just showing you that there's nothing magical about these wrapper classes. Essentially, all they're doing is, again, in the constructor acquiring a resource and in the destructor releasing it. So it's completely possible if we wanted to build our own implementation of one of these wrapper classes. But thankfully, C++ already has some built in for us. So you will be seeing these three terms, especially unique pointer and shared pointer, pretty much everywhere in C++ code nowadays where you would be using pointers. And we'll be going through these one by one. Turns out there's also a bunch of other smart pointers, in this case from those extra libraries called the boost libraries that we mentioned earlier. There's also something that you may see called an auto pointer, but that was actually deprecated in C++ 11 and completely removed from C++ 17. So yeah, basically you never want to be using auto pointer. But this was actually introduced in C++ 98, which just shows how far back the C++ creators were thinking about this idea of RAII and an exception-safe code. Okay, so what is a unique pointer? A unique pointer is, you can basically think of it as the equivalent of a lock guard, except for pointers. So it will uniquely own its resource, like a permission slip, as Avery was saying, and it will delete it in the destructor when the object is destroyed. And we will get back to the cannot be copied soon. So again, whereas before we had this explicit new and delete, now we can use the C++ class called a unique pointer, which guarantees that when the object itself goes out of scope, the memory will all be freed. Does anyone have an idea of why this cannot be copied? Sort of similar to what Avery. Yes, bring in the back. Exactly. Well, say that one more time. If you could copy it, then it wouldn't be. There we go. Exactly. It wouldn't uniquely own a resource. And to give you an idea of why that would be such a bad thing, let's say we did try to copy unique pointers. So let's say we had a unique pointer to some data on the heap, and let's say we were able to copy it. So we had some copy y that still pointed to the same data on the heap. Then let's say y goes out of scope and deletes the heap data with it, because again, whenever the destructor is called, it deletes whatever it's pointing to. Then what happens to x? Well, if we then try to dereference x, and or when x goes out of scope, then when it tries to delete the data on the heap, it's no longer there to be deleted. And so you'll crash, and there's a whole, this is known as like a double free essentially, and there's a whole other range of security bugs that actually come from that as well. And we're sad. Okay, so that is why this class, unique pointer, disallows copying. And as an aside, as review, how is it that you can tell a class to disallow copying? How do we syntactically be able to do that? Yeah, go for it, Brian.
In the copy constructor, the destructors, you just like tell it to die.
So that's one way you could manually tell it go die in the copy constructor destructor. Turns out there's actually a way that you can do it syntactically before. I didn't actually write the syntax here, but Avery actually showed it in a previous slide today for, I believe, the implementation of the lock guard. So there you'll see that you can, again, just as you can make a constructor and set it equal to default, you can also set a constructor equal to delete, and that will delete it. And you might see that a lot of times if you try going and exploring like your Stanford code, you'll see for a lot of classes they've done something called like deleting the copy constructor and copy assignment. Yeah, so that's just the syntactical side of how you go about deleting. But this is a problem because if say you've been working with code, you might realize that, okay, sometimes I do want to have multiple pointers to the same object. Like why should I only have to have one pointer to an object? It almost seems to defeat the purpose of pointers. It seems very much less flexible. Yes, well, I did not copy over those changes, but our answer is C++ has already anticipated that. There's in fact another class of smart pointers called a shared pointer. So as brief background, the purpose of a shared pointer is to do the same RAII compliance to ensure that a resource is always deleted, but in this case, that resource can be shared by any number of shared pointers, and it's deleted only when none of them point to it. An example use case syntactically of this might be, let's say we declare a shared pointer to this new int called p1, and then let's say, you'll notice here we're using what Avery mentioned of that inner scope, where we're just using 2 braces to indicate that this should be some separate scope. In this case, we declare another shared pointer, and notice that to declare another shared pointer, we use a copy constructor. So in this case now we have both p1 and p2. We hit this line, and p2 goes out of scope, and then we hit this line, p1s go out of scope, and then finally, now there are no pointers referring to that new int, and so the int is freed. Does that make sense? Does anyone have any questions about the shared pointer? Okay, so one question that you might have is, yes, and again, important, the way that you want to declare shared pointers is after you've created the first one, declare all subsequent ones using the copy constructor. So one question might be, how are these implemented? Like, why is it that the unique pointer doesn't do the same thing? It turns out there's this technique known as reference counting, where it's essentially follows what your intuition says it does, which is, let's say in our shared pointer class, let's have some sort of count that keeps track of how many pointers to that same heap data exist. And so sort of practically the way that you would do that is just every time the copy constructor or copy assignment gets called, you increment that count by 1, and then every time any destructor is called, you decrease it by 1. And then finally, you free the heap data only when the reference count hits 0. So in our previous example, oops. All right, so in our previous example, up here, when P1 is declared, we'll set our reference count equal to 1. Up here, the copy constructor is called, so we'll increment that to 2. Here, P2 destructor is called, so we decrease it back to 1. And then finally here, the P1 destructor is called, so it decreases to 0. And then therefore, we know that we can delete the heap memory safely. Does anyone have any questions on that? No. Awesome. Okay, so I'm going to do, I'll finish up a bit of this, and then we can finish the rest in our final lecture. So the first is, notice that our previous example, where we used a unique pointer to do our previously non-RAII compliant function, still works. Instead of a unique pointer, we could use a shared pointer, and actually this function would still work perfectly fine. Why is that? Why can we use a shared pointer here and it still works? Yeah, Zach, go for it.
It just still hit 0 references at the end of the code.
Perfect, exactly. So for a shared pointer, you don't have to have more than 1 reference, but it does allow you to have more than 1. Exactly, perfect. Awesome. And then, so finally, it turns out there's actually something known as a weak pointer in C++. What it does is it's similar to a shared pointer, but it doesn't increment your reference count. So it allows you to have another reference, but it won't increase your reference count, and that's okay because of some other implementation details of weak pointer. We won't get too much into this because this is extra material, but if you're interested in using something like that, now that you know what it's supposed to do, feel free to look at the C++ documentation, and you'll understand sort of the details of how to use it. Okay, so I'm going to cover this last part next time. One thing that we want to do before we go is Avery will be out of town on Thursday. So if Avery would like to explain.
Hi. So I have a tradition where I take a selfie with everyone, so please. Thanks. And yeah, you get confused. You're in, how many people are here? 15? 15 out of 50. Okay, yeah. So I was at the beginning of the quarter. I was thinking, okay, this selfie is gonna be hard, but then it's not actually even more difficult than a normal section. Because in section, people usually show up. All right, come on forward. Where do you think we should take the photo? Here, or here, or
that, or you want
face
to face here?
We can get people to sort of sit on the steps.
Yeah, this way we take care of the
Okay.
heights. Yeah.
but it's kind of, but it's kind of right though.
Oh,
Yeah.
I got you.
Oh. Okay, there we go. All right. Everyone.
Oh, yeah. All right, you guys. Smile. If you can see the camera can see you.
All right, is everyone in the camera? You sure? Everyone's in the camera? Okay, I'll just take a lot of photos, and one of them, everyone's eyes will be open. Okay, a silly photo?
I'm always.
Wait, we want to do
Okay, fine, serious photo. Serious. Okay, silly photo. A quick question: did you bring that just for the selfie?
No, it's
That's
not.
Okay, cool. All right,
Just
one
service.
more. How do you feel about the 106 year X final? Go.
I'm not taking
Wait,
it.
midterm.
Okay, midterm, sure.
Hard pass, hard pass.
All right. Thank you.
Okay, good
Thank
job.
you, everyone.
Okay, and before you go, so the logistics for the last lecture, traditionally what we do is we're going to send out a survey, or we meaning now me, and are going to send out a survey about what topic you guys want me to cover in the last lecture. So this can be anything. It can be like multi-threading, it can be blockchain, for some reason has always been popular. But the key thing is you want to return